Hello students, I hope you all are doing good. Today we will discuss NCERT section 13.7 and example 13.4 of chapter nuclei. This is the disclaimer. Today we are focusing on what you will be able to do after this lecture about nuclei. These are our learning goals, so keep them in mind as we go through the material. Let's start with the first goal, understanding the basic principles of nuclear fission and fusion. Fission is when a heavy nucleus splits into smaller parts, releasing energy, while fusion is when light nuclei combine to form a heavier nucleus, also releasing energy. Both processes follow conservation laws like conservation of energy and conservation of charge. Differentiate between nuclear and chemical reactions in terms of mass energy conversion and comprehend their practical applications in energy generation. Today we are starting our discussion on nuclear energy, which is a major topic in modern physics. Nuclear energy comes from the nucleus of atoms and can be released in two main ways, fission and fusion. We will discuss NCERT section 13.7.1, that is nuclear fission. Further, we will talk about chain reactions. In a chain reaction, the products of one fission event can trigger more fission events, leading to a rapid release of energy. Next, we move on to nuclear fusion, which is the process that powers stars, including our sun. Then we will look specifically at the proton-proton cycle, which is the main fusion process in stars like sun. In this cycle, 4 protons combine through a series of steps to form a helium nucleus, releasing energy, positrons and neutrons. This process is responsible for the sun's energy output and is crucial for life on Earth. Next, we will discuss controlled thermonuclear fusion. Scientists are working to replicate the fusion process on Earth to create a clean and virtually limitless energy source. Finally, we will look at example 13.4, which will help us apply these concepts to a real world problem. We will work through the numbers and see how the principles of nuclear energy play out in practice. Let's start by looking at the objective, that is understanding nuclear energy. Notice the image of nuclear power plant. This is the real world application of nuclear energy. Now let's define nuclear energy. Nuclear energy is the energy released during nuclear reaction such as fission and fusion. These are processes that happen inside the nucleus of atom and they release a huge amount of energy compared to the chemical reactions like burning fuel. This energy release is explained by a principle of mass energy equivalence, which is given by the formula E equal to mc square. Here E stands for energy, m is mass and c is speed of light. The binding energy per nucleon curve helps us understand why some nuclei release energy when they split or combine. These are two types of processes: nuclear fission, nuclear fusion. First, nuclear fission is when a heavy nucleus like uranium-235 splits into two smaller nuclei, releasing energy and more neutrons. Next, nuclear fusion is when two light nuclei such as hydrogen isotopes combine to form a heavier nucleus, also releasing energy. Let's start by understanding nuclear fission. Notice the diagram in the center. This shows a heavy nucleus splitting apart. Nuclear fission is a key concept in nuclear physics and is the basis for both nuclear reactors and atomic bombs. We will break down what happens during this process step by step. Now let's define nuclear fission. Nuclear fission is the process where a heavy nucleus such as uranium splits into two or more lighter nuclei when it is hit by a neutron. This splitting doesn't create new elements, it also releases a lot of energy. Notice that when fission occurs, a tremendous amount of energy is released. This energy comes from the conversion of a small amount of mass into energy. as described by the equation E equal to mc square. This huge energy release is why nuclear fission is so important for both power generation and weapons. Okay, so nuclear fission, heavy nucleus don't just split into two or more lighter nuclei, it also releases huge amount of energy. Let's understand the reactions involved in nuclear fission. Now let's look at the specific reaction for uranium 235 when a neutron, which we write as N with mass number 1 and atomic number 0, hits a uranium 235 nucleus. It forms a uranium 236, which is unstable. This unstable nucleus then splits into two smaller nuclei, barium 144 and krypton 89, plus three more neutrons. The reaction can be written as neutron plus uranium 235 leads to uranium 236 leads to barium 144 plus krypton 89 plus 3 neutrons. Notice how the numbers balance on both sides. This shows conservation of mass and charge. Mark it as equation 3.10. Let's break down what happens during nuclear fission. When a uranium 235 nucleus absorbs a neutron, it becomes unstable and splits into two lighter elements called fission products. This splitting releases a lot of energy and also produces more neutrons. These extra neutrons can hit other uranium 235 nuclei, creating a chain reaction. This is the basic principle behind how nuclear reactors and atomic bombs work. The key step is that the neutron collides with uranium 235, forming uranium 236, which is highly unstable. This unstable nucleus quickly splits into two smaller nuclei, releasing energy and more neutrons. The process is self-sustaining if enough uranium 235 is present, because the released neutrons can keep the reaction going. Let's look at the main reaction for uranium 235 when a neutron, which we write 1N, hits a uranium 235 nucleus. It forms uranium 236, which is unstable. This unstable nucleus then splits into two smaller nuclei, barium 144 and krypton 89, plus 3 more neutrons. During this splitting or fission, 2 to 3 extra neutrons are released along with a huge amount of energy. This energy comes out as heat and radiation. For example, the energy released in one fission event is about 200 million electron volts, which is much more than typical chemical reaction. Notice that released neutrons can go on to hit other uranium 235 nuclei. This can start a chain reaction where each fission causes more fissions. If enough uranium 235 is present, this reaction can sustain itself, releasing more and more energy. This is how both nuclear reactors and atomic bomb work. But reactors control the chain reaction while bombs let it run unchecked. The reaction doesn't always produce the same fragments. Sometimes uranium 235 splits into other pairs of intermediate mass nuclei. For example, it can produce antimony 133 and niobium 99 along with 4 neutrons. The exact products depend on how the uranium nucleus splits, but the total number of protons and neutrons is always conserved. This is equation 13.11. So more examples: when a neutron hits uranium 235, it splits into xenon 140 and strontium 94 plus 2 more neutrons. This is equation 13.12. Finally, the fragments produced by fission are usually radioactive. They emit beta particles, which are high energy electrons, as they decay to become more stable. This process of beta decay continues until the fragments reach stable forms. The radioactivity of this product is an important consideration for nuclear waste management and safety. Let's understand how energy is released during nuclear fission. Let's start by looking at the energy released in a typical fission event. The energy released, often called as Q value, is about 200 mega electron volt for each fission event. This energy doesn't just appear in one form, most of it shows up as kinetic energy, the motion of fission fragments, and the neutrons that are released. Some of the energy is also emitted as gamma radiation, which is a very high energy form of light. So the energy from fission is shared among these different products. Now let's consider a specific example. Imagine a nucleus with mass number A equal to 240 splitting into two fragments, each with mass number 120. For the original nucleus with A equal to 240, the binding energy per nucleon, which we called EBN, is about 7.6 mega electron volt. Binding energy per nucleon tells us how tightly each nucleon is held within the nucleus. The higher this value, the more stable the nucleus. For the two resulting fragments, each with A equal to 120, A is mass number here, the binding energy per nucleon increases to about 8.5 mega electron volt. This means that nucleons in the smaller nuclei are held together more tightly than in the original larger nucleus. So the gain in binding energy per nucleon is about 0.9 mega electron volt. The increase in binding energy per nucleon is what derives the release of energy. To find the total energy released, we multiply the gain per nucleon by the total number of nucleons, 240 times 0.9 mega electron volt, which gives us 216 mega electron volt. This calculation shows us why nuclear fission releases so much energy. It's all about the increase in binding energy when a heavy nucleus splits into smaller, more stable ones. Let's start by understanding the concept of a chain reaction. Notice the diagram in the center of the slide. This will help us visualize how a chain reaction works in nuclear physics. A chain reaction is a process where the products of one reaction event causes the additional events to occur, leading to a self-sustaining sequence. Now let's examine what happens during nuclear fission in uranium-235. When a single neutron collides with a uranium-235 nucleus, it causes the nucleus to split or undergo fission. The reaction releases 3 new neutrons along with 2 smaller nuclei, barium-144 and krypton-89. The numbers indicate the atomic and mass numbers. Notice that the process releases more neutrons than it started with. This is key to the chain reaction. These newly released neutrons can then go on to strike other uranium-235 nuclei, causing them to split as well and release even more neutrons. This creates a multiplying effect where each fission event leads to more reactions. This is what we mean by a chain reaction. One event triggers a series of similar events. Now let's focus on what actually happens during a chain reaction. Each of these new created neutrons in fission process can cause more fission events, leading to a rapid multiplying release of energy. This is why chain reactions can grow so quickly. In the fission of uranium-235, on average 2.5 neutrons are released per fission event. These neutrons released can go on to hit other uranium-235 nuclei, causing them to split as well. This process where one reaction leads to many more is what we call a chain reaction. Building on that, in a nuclear chain reaction, the neutrons released from one fission event trigger more fissions in other nuclei. Let's introduce a key term, critical mass. Critical mass is the minimum amount of fissile material like uranium-235 needed to keep a chain reaction going. If you have less than this amount, the reaction will die out because not enough neutrons are available to sustain it. If the mass of fissile material is too small, what we call subcritical, too many neutrons escape without causing further fission. This means the chain reaction can't continue. So achieving and maintaining critical mass is essential for a sustained nuclear reaction. So types of chain reactions. First, let's talk about uncontrolled chain reactions. In this case, the number of fissions increases exponentially in a very short time, releasing a huge amount of energy all at once. This is what happens in a nuclear bomb, where the reaction is not managed and leads to massive explosion. Next, we have controlled chain reactions. Here, the rate of fission is carefully managed so that on average, only one neutron from each fission event causes another fission. This keeps the energy release steady and safe, which is how nuclear reactors generate electricity. Let's understand nuclear fusion. Notice the image in the center. It shows two light nuclei coming together to form a heavier nucleus. Now let's define nuclear fusion. This is the process where two or more light atomic nuclei combine or fuse to form a single heavier nucleus. It's the opposite of nuclear fission, where a heavy nucleus splits into two lighter ones. Fusion is the responsible for energy produced in stars. Why does fusion release energy? It's because the binding energy per nucleon, that's the energy holding each proton and neutron together in the nucleus, is greater in the product nucleus than in the original, lighter nuclei. This difference in binding energy is released, often as heat and light. For example, when hydrogen nuclei fuse to form helium in the sun, a huge amount of energy is released. But fusion doesn't just happen anywhere. Certain conditions are needed. Let's look at what those are. So, first is extreme temperature. To be specific, the temperature required is around 1 billion Kelvin or 10 to the power 9 Kelvin. At this temperature, the kinetic energy of the nuclei is high enough to overcome their mutual repulsion. For comparison, the core of the sun is about 15 million Kelvin, which is still extremely hot by Earth standard. The second condition is extreme pressure. High pressure increases the density of the plasma, which means the nuclei are packed closer together. This raises the probability that they will collide and fuse. In stars, gravity provides both the high temperature and high pressure needed for the fusion. To sum up, these extreme conditions, high temperature and pressure, exist naturally in the cores of stars. That's why fusion is called thermonuclear fusion. Thermo for heat and nuclear for the atomic nuclei involved. Now let's understand nuclear fusion reactions. Nuclear fusion is the process where two light atomic nuclei combine to form a heavier nucleus, releasing energy in this process. Let's start by looking at some specific nuclear fusion reactions. These reactions involve light nuclei like hydrogen coming together under certain conditions. So in the first reaction labeled 13.13a, two protons, these are hydrogen nuclei, combine to form a deuteron, which is a hydrogen nucleus with one proton and one neutron. Along with the deuteron, a positron and a neutrino are produced, and 0.42 mega electron volt of energy is released. This reaction is the first step in the fusion process that happens in stars like our sun. Now in reaction 13.13b, two deuterons, each with one proton and one neutron, combine to form a helium-3 nucleus, which has two protons and one neutron, plus a neutron is released. This reaction gives a 3.27 mega electron volt of energy. Notice how the energy released here is much greater than in the previous reaction, showing that as the nuclei get heavier, the fusion process can release more energy. In reaction 13.13c, two deuterons fuse to form a triton, which is hydrogen nucleus with one proton and two neutrons and a proton. This reaction releases 4.03 mega electron volt of energy, which is even higher than the previous two. These examples show us the variety of products and energy outputs possible in fusion reactions. Let's examine the first requirement for fusion. For two nuclei to fuse, they must get extremely close to each other, close enough for the short range nuclear force, which is a very strong attractive force, to pull them together. This force only acts over distances about the size of an atomic nucleus, which is roughly 1 femtometer or 10 is per minus 15 meters. However, notice that both nuclei are positively charged, so they naturally repel each other due to the Coulomb force, also called electrostatic repulsion. This repulsion force gets stronger as the nuclei get closer, making it very difficult for them to approach other. This is why fusion doesn't happen easily at normal temperatures and pressures. So for fusion to actually take place, the nuclei must have enough kinetic energy to overcome this Coulomb barrier. The energy needed to push through the new electrostatic repulsion in stars, this is achieved because the temperature are extremely high, giving the particles enough speed. Now our objective is to understand the proton-proton cycle in stars. This is fundamental process that explains how star like our sun produces energy. Let's start by looking at thermonuclear fusion. This is the process that generates energy inside stars. In simple terms, thermonuclear fusion means that nuclei combine at extremely high temperature, releasing a huge amount of energy. Interior of the sun has a temperature of 1.5 times 10 to the power 7 Kelvin, which is considerably less than the estimated temperature required for fusion of particles of average energy. Next, let's how fusion happens in the sun. It's not a single step reaction but a multiple step process. In this process, hydrogen nuclei are gradually converted into helium nuclei. Each step releases energy, and together these steps make up what we call the proton-proton cycle. It's important to remember that the sun's main fuel is hydrogen, which is found in its core. As hydrogen is fused into helium, the sun continues to shine and provide energy. So today's our objective is to understand the proton-proton cycle in stars. This is a fundamental process that powers stars like our sun by converting hydrogen into helium and releasing energy. As we go through the steps, pay attention to how small particles interact to produce the energy that makes stars shine. Let's start by looking at proton-proton cycle. This is the main set of nuclear reactions that allow star to fuse hydrogen atom together. Notice that these reactions involve protons, which are the nuclei of hydrogen atoms, coming together under extreme conditions inside stars. Let's see the first reaction, where two hydrogen nuclei combine to form deuteron along with a positron and neutrino by releasing 0.42 mega electron volt energy. In second reaction, a positron and electron combine to form two gamma rays and 1.02 mega electron volt energy is released. In third reaction, a deuteron and proton combine to form helium-3 nucleus along with gamma ray and 5.49 mega electron volt energy is released. In final equation, two helium-3 nuclei combine to form an helium-4 nucleus, two hydrogen nucleus along with 12.86 mega electron volt of energy. For the fourth reaction to happen, the first three reactions must occur twice. This means we need two helium-3 nuclei which then unite to form regular helium-4 nucleus. This step is crucial because it completes the cycle and allows the process to keep going, producing more energy and helium. If we add up all these reactions, 2 times each of the first 3, plus the fourth, we get the overall effect of the proton-proton cycle. This helps us to see the big picture, how many particles go in, how many come out, and how much energy is released in total. The net result is that 4 hydrogen nuclei and 2 electrons combine to form one helium-4 nucleus, 2 neutrinos, 6 gamma rays, and 26.7 megaelectron volt of energy. This shows us how stars convert hydrogen into helium and release huge amount of energy, which is what powers their light and heat. Let's look at the overall reaction for the proton-proton cycle. 4 hydrogen nuclei, which are protons, and 4 electrons combine to form one helium-4 nucleus, 2 positrons, 2 neutrinos, and 6 gamma photons, and about 26.7 million electron volt of energy. Notice that sun's energy comes from mainly proton-proton cycle. In this process, hydrogen atom fuse together to make helium. Without this cycle, the sun wouldn't be able to shine or support life on Earth. Now let's focus on the energy released. The total energy output from one complete proton-proton cycle is about 26.7 mega electron volt. To put this in perspective, 1 mega electron volt is 1.6 times 10 to the power minus 13 joules. So this is a huge amount of energy for just a few atoms. This energy is carried away by the particles produced, especially the gamma rays, which eventually heat the sun and make it shine. As stars run out of hydrogen in their cores, their core temperature increases due to gravitational collapse. This higher temperature allows the fusion of heavier elements, so stars can make elements heavier than helium like carbon and oxygen. Elements beyond a certain mass, those beyond the peak of the binding energy curve, cannot be produced through fusion. The sun has been shining for about 5 billion years and still has enough hydrogen to keep fusing for another 5 billion years. This long lifespan is due to the slow and steady rate of fusion in the sun's core. It's the good reminder of how stable and long lasting our star is. Eventually, when sun runs out of hydrogen, its core will contract and heat up while the outer layers expand. This will turn the sun into a red giant, a much larger and cooler star. Now let's see controlled thermonuclear fusion. This is a process where we try to harness the same kind of nuclear reactions that power the sun, but in a controlled way here on Earth. Let's examine how thermonuclear fusion reactors work. They try to copy the fusion process that helps naturally in stars by heating thermonuclear by nuclear fuel to extremely high temperatures, about 100 million Kelvin. To give you an idea, that much hotter than the core of the sun and far beyond anything we experience on Earth. At these temperatures, the fuel doesn't stay as a solid, liquid, or gas. It becomes plasma. Plasma is a special state of matter made up of positive ions and free electrons. Notice the main challenge here: containing this superheated plasma, no physical material can touch it without melting instantly. So scientists use magnetic fields to keep the plasma suspended and away from the walls of the reactor. To sum up, many countries, including India, are investing in fusion research because we could provide nearly unlimited clean energy in the future. If we can solve the technical challenges, fusion reactors could change how we power our world. Let's examine the question. These are conceptual questions about nuclear reactions, mass energy conversion, and how these ideas compare to chemical reactions. So part A is, are nuclear reactions balanced like chemical equations? So this question tests your understanding on what it means for an equation to be balanced in physics versus chemistry. In chemistry, equations are balanced by making sure the number of atoms on each element is the same on both sides. In what sense nuclear reactions are then balanced on both sides? Part B. This question asks you to think about how mass can be converted to energy even when the number of protons and neutrons stay the same. It tests your understanding of Einstein's mass energy equivalence equal to mc square, where E is the energy, m is the mass, and c is the speed of light. Notice how the question wants you to connect the idea that even if particles are conserved, their total mass can change, with the difference appearing as energy. Part C. Mass energy interconversion in chemical versus thermonuclear reactions. This question challenges the common belief that only nuclear reactions involve mass energy conversion. It tests your understanding that, according to physics, all reactions involve tiny changes in mass that corresponds to energy changes. But these are much smaller in chemical reactions. First, let's focus on how part A of the question is being solved. We are being asked whether nuclear equations are balanced in the same way as chemical equations, and if not, what exactly is balanced in the nuclear reaction. A chemical equation is balanced in the sense that the number of atoms on each element is same on both sides of the equation. Chemical reactions only change how atoms are combined, they don't change the actual atoms themselves. The atoms are simply rearranged into new molecules, but the total number of each type of atom stays the same. In contrast, nuclear reactions can actually change one element into another. This process is called transmutation. For example, when uranium 238 decays, it turns into thorium 234, which is completely different element. So nuclear reactions, the number of atoms of each element is not necessarily conserved. Instead, what is conserved are the total number of protons and neutrons, as well as charge and energy. First, notice that in nuclear reactions, the number of atoms of each element is not conserved, unlike chemical reactions, where the same atoms just rearrange. Nuclear reactions can actually change one element into another. However, even though the atoms themselves may change, the number of protons and number of neutrons are each conserved separately in a nuclear reaction. This means that if you count all protons and the neutrons before and after the reaction, the total will be the same. At very high energies, even the conversion of protons and neutrons can break down, but what is always conserved is total charge and something called baryon number. For our purposes, we don't need to go into detail, but it's good to know that these deeper conversion laws exist in physics. Let's look at specific example. In the reaction where a neutron hits uranium 235, it produces uranium 236, which then splits into barium 144, krypton 89, and 3 neutrons. If you add up the protons and neutrons on both sides, you will see they match. This shows how nuclear equations are balanced, not by atoms but by the number of protons and neutrons. Let's focus on part B of the question. Here we are being asked to explain how mass is converted into energy during nuclear reactions, even though the number of protons and neutrons doesn't change. To answer this, remember that the binding energy of a nucleus is the energy that holds the nucleus together. This binding energy actually reduces the total mass of the nucleus compared to the sum of individual masses of its protons and neutrons. This difference is called the mass defect. Now, even though the total number of protons and neutrons is the same before and after the reaction, the total rest mass of all the protons and neutrons on both sides is also the same. This means that the basic building blocks are conserved, but something else must account for the energy released or absorbed. However, the total binding energy of the nuclei on the left side of the reaction doesn't have to be equal to the total binding energy on the right side. This difference in binding energy is what allows nuclear reactions to release or absorb energy, even though the number of protons and neutrons stays the same. So the key point is that the difference in binding energies between the reactants and the products shows up as energy released or absorbed in the reaction. This energy can be calculated using E equal to mc square, where E is energy, m is the mass defect, and c is the speed of light. First, notice that difference in binding energies between the reactants and products in a nuclear reaction is what leads to the energy being released or absorbed. Binding energy is the energy that holds the nucleus together. Since binding energy actually contributes to the mass of a nucleus, any difference in the total binding energy between the two sides of a nuclear reaction means there will be a difference in mass. This difference in mass gets converted into energy, or energy can be converted into mass according to famous equation E equal to mc square. So nuclear reactions are a clear example of mass energy interconversion. This means that mass can be transformed into energy and vice versa. Let's start by examining why belief that mass energy conversion only happens in nuclear reactions is not completely correct. Notice that in principle, chemical reactions also involve mass energy interconversion, just like nuclear reactions. The main difference is that the amount of energy involved in chemical reactions is much smaller, but the underlying principle is the same. The energy released or absorbed in a chemical reaction comes from the difference in chemical binding energies between the reactants and the products. Chemical binding energy is the energy that holds atoms together in the molecules. When this energy changes, it can result in either the release or absorption of energy. Now let's focus on mass defect. Even in chemical reactions, the chemical binding energy contributes a small negative amount to the total mass of atoms or molecules. This means that the mass of a molecule is actually slightly less than the sum of masses of its separate atoms due to the binding energy. So we can say that the difference in total mass of atoms or molecules before and after a chemical reaction is converted into energy or vice versa. This is just like what happens in nuclear reactions, but the effect is much smaller in chemical reactions. Now let's focus on the idea that mass energy conversion can happen in chemical reactions too. The difference in total mass between the atoms or molecules before and after a chemical reaction is actually converted into energy, or energy can be converted into mass. However, the amount of mass lost or gained in chemical reaction is extremely small, almost a million times smaller than what we see in nuclear reactions. This means that the energy released or absorbed due to mass change in chemical reaction is usually too small to notice. So the common belief that the mass energy conversion doesn't happen in chemical reaction is actually incorrect. It does not happen because the effect is so small that we usually ignore it. To sum up, mass energy interconversion is a universal principle, but it's only significant in nuclear reactions because of the much larger mass changes involved. Let's summarize the topic that we have discussed today. Nuclear fission means splitting a large heavy nucleus into smaller lighter nuclei, and this usually happens when the nucleus is hit by a neutron. Now let's look at specific example, uranium 235. When uranium 235 undergo fission, it can break into different pair of medium sized nuclei called intermediate mass fragments, and it also releases extra neutrons. Each time a fission event happens, about 200 million electron volts or 200 million or 200 mega electron volts of energy is released. To put this in perspective, 1 electron volt is a tiny amount of energy, so 200 mega electron volt is a huge amount of for a single atom. The nuclear chain reaction happens because the neutrons released from one fission event go on to trigger more fission events in other nuclei. If this process keeps going, it can lead to a rapid self-sustaining reaction. Critical mass is the smallest amount of a material that can sustain a nuclear chain reaction on its own. This is important in nuclear physics because if you have less than the critical mass, the reaction will stop by itself. Fusion is when two light atomic nuclei combine to form a heavier nucleus, and this process releases a lot of energy. For fusion to happen, extremely high temperatures and pressure are needed. This is because the positively charged nuclei naturally repel each other. So you need a lot of energy to force them close enough to combine. In stars, the temperature is about 100 million Kelvin, much hotter than anything we can easily create on Earth. One example of fusion in stars is the proton-proton cycle. In this process, hydrogen nuclei are converted into helium, and each cycle releases about 26.7 million electron volts of energy. Chemical reactions like burning fuel involve much smaller change in mass and energy compared to nuclear reactions. This is why nuclear energy is so much powerful than chemical energy, even though both involve changes at atomic levels. Both nuclear and chemical reactions follow the law of conservation of mass energy, which means the total amount of mass and energy stays the same before and after the reaction. However, it's important to notice that nuclear reactions involve larger changes in energy compared to chemical reaction. Now let's look at what is conserved in nuclear reactions. In these reactions, the number of protons and neutrons is always conserved, but the actual element can change. This process is called transmutation. Energy. Next, we talk about the energy in nuclear reactions come from. The energy releases or absorbed is due to differences in nuclear binding energies. Binding energy is the energy that holds the nucleus together. When nuclei combine or split, the total binding energy changes, and this difference shows up as released or absorbed energy. Finally, let's consider the potential of controlled thermonuclear fusion. If we developed technology to control fusion reactions, we could have a nearly unlimited source of clean energy. Let's see some practice questions based on today's topic. Let's look at nuclear fission, specifically with uranium 235. The first question asks about the average number of neutrons released per fission event. Second question is that which process needs a minimum critical mass to keep the reaction going? Nuclear fission or nuclear fusion? Next question asks about the nuclear fusion and what conditions are necessary for it to happen. Here we are asked to write the nuclear equation for deuterium fusion that produces helium-3 and a neutron. Finally, let's look at the proton-proton cycle in stars like our sun. The question asks for the final product when hydrogen nuclei fuse. So this is all about today's lecture. I hope you enjoyed the session. Thank you for your attention.